Let me show you one more amplifier op-amp topology. All right, this is called, well, I'll name it at the end. Let's return to our, what should start to look familiar, this R2, R1, going back to the negative terminal. I should point out that negative feedback can be spotted by following a path from V out to V minus. All right, so in this case it's R2. This case R2 is what provides the negative feedback. All right, if I had something like this, okay, this is positive feedback. Why? Because the output VO is being fed back, but not to the negative input. It's being fed back to the positive input, and so that actually produces positive feedback, which has a very different result. So we're kind of in this sandbox now, in this discipline of negative feedback. So all the op-amp circuits that we'll be solving for the time being all use negative feedback. But you always want to check that. A tricky question would be if I gave you a circuit that actually looked very familiar, like one of these circuits we've already solved, but I wired it up such that it had positive feedback and asked you a question about it. You know, you might just dive right in assuming it's negative feedback, but if you'd stop and say, okay, let's see, is there negative feedback? Well, no, there isn't. Therefore, I can't possibly have this, you know, for the inverting amplifier, it would not be minus R2 over R1 for the voltage gain, because that only applies when I have negative feedback. Okay, so we have, what we've done in the previous example was we had an input VI, I'll call it V1 here. And we found that VO was minus R2 over R1 V1. All right. We've also had this circuit here where we have connected R1 to ground, and we have applied a voltage, I'll call it V2, to our non-inverting. That's a term that's used. I haven't used those yet, but non-inverting input. That's just a fancy word for the V plus, the positive input. This is the inverting input. All right, that just means the V minus. We found that VO in this case was equal to 1 plus R1 over R2 times V2. All right. Now, what if we had both inputs applied at the same time? I'll redraw this. R2, R1. We have our input V1. And now we have this input V2. Now I'm going to claim by superposition, because this is a linear circuit, that VO will be equal to 1 plus R1 over R2 V2 minus R2 over R1 V1. So I'm just putting those two together. But let's not assume that for a minute. Let's practice this analysis again. So I'm going to redraw this. Eventually you won't have to redraw it, but I'll just do this for clarity since this is new to you. I've got R1 and R2. At this end here, I've got V1. At the other end, I have V out. In the middle, I have V minus. But V minus is equal to V plus. Right? Because this is an ideal op-amp and I have negative feedback, I can claim V minus is equal to V plus. So the inverting input is equal in voltage to the non-inverting input voltage. And because V plus in this case is not tied to ground, as it is for the inverting amplifier, but it's tied to V2, I therefore can claim that V minus, this voltage here, must equal V2. Right? And what I'm going to show you, what I'm trying to show you, is this superposition analysis that we just did for the inverting op-amp will be almost the same here, but this is a different topology. And hopefully it drives home the point of how useful and simple it is to solve op-amp circuits if you use this type of technique. So what am I going to do? I'm going to write the same superposition expression for V minus, which is R2 times V1 plus R1 times VO over R1 plus R2. Right? The only thing that changes from the inverting amplifier analysis that we did previously is that now V minus, instead of being equal to 0 as it was before, V minus is going to be equal to V2. Okay? So, okay, we'll write it this way, R1 VO, and I'm going to, let's rewrite it here, R1 plus R2 times V2 minus R2 times V1 is equal to R1 times VO. And let's solve for VO. So we have R1 plus R2 over R1 times V2 minus R2 over R1 times V1. And I can rewrite that as 1 plus R2 over R1 V2 minus R2 over R1 V1. And lo and behold, that is, in fact, what we found up here. Now I want to do one other thing to make this circuit much more useful. Suppose I add another resistor in here, or two more resistors. Suppose I have V1 here, R1 and R2. But now, instead of feeding V2 directly, I'm going to feed it through a voltage divider. Okay? And I'll say this is R3 and R4. Now I don't need to go through a bunch of analysis to solve this. I can write it by inspection. The reason I can write it by inspection is because there's no current flowing into I plus or V plus. I can state right away that V plus, the voltage at the non-inverting input, is now just a voltage division version of V2. It's going to be R4 over R4 plus R3 times V2. And so I can simply replace the V2 in the previous exercise right here, this guy. I can replace him with the voltage divided version like so. Alright, this voltage here is just R4 over R4 plus R3 times V2 minus R2 over R1 V1. Now that looks messy at first, but suppose that R3 was made equal to R1 and R4 was made equal to R2. Then this simplifies significantly, because after all, this I can write as R1 plus R2 over R1. All right? And now what I have is, I see that a bunch of things will cancel. I have R1 plus R2 will be equal to R3 plus R4. So, and R4, so these will cross out right here. And this is just R2, right? And so what I end up with is R2 over R1 times V2 minus V1. And this voltage here, what I'll call this input, I'll call it this way here. I'll say this is VI. And VO is now equal to R2 over R1 times VI. Okay? And what is significant here is that suppose V1 was equal to 10, or let's say V2. V2 was equal to 10.01 volts. And V1 was equal to 10.00 volts. And R2 over R1 was equal to 100. Right? Then VO would be equal to the difference between the two voltages, which would be 0.01 volts, times R2 over R1. So it would be 100 times 0.01, or 1 volt. In other words, what this amplifier is what's called a difference amplifier. A difference amplifier. It takes the difference between two voltages, V2 and V1, and amplifies only what's different between them. Doesn't amplify the voltage that's common. So in this case, I guess if I had written, if we had 10.01 for V2 and 9.99 for V1, right, the voltage that would be in common would be 10 volts. One would be 0.01 above it, one would be 0.01 below it, and the difference then would be 0.02. And when I amplify that, I would get 2 volts at the output. And that is a very useful circuit. If you think, let me go to one more little sketch here. Suppose I have a battery, all right, and I'm wanting to measure, I have some load over here. Who knows what it is? And I have current that's flowing into here, and I want to measure this current. If I had a resistor up here, let's say it was a 10 milliohm resistor, one way I could measure this voltage would be, or measure the current, I'm sorry, is to look at this small voltage drop that's across this shunt, we'll call a shunt resistor. The shunt resistor is a small resistor whose purpose is just to produce a tiny voltage, a voltage that's much, much smaller than the voltage of the source from where this current is flowing. And that voltage is to be proportional to the current, and so you can actually measure current indirectly by looking at the voltage. Well, how could we measure this? We could come in with a difference amplifier. Oops, minus and plus. Okay, and we'd have R2 and R1, and if we give this the same value, right? So we wanted to measure something that was going to be up to 10 amps, 0 to 10 amps. Okay, 10 amps would produce a 100 millivolt drop, right? 10 amps times 10 milliohms would be 100 millivolts. And let's say that I wanted an output that went from 0 to 10 volts. Right? So 10 volt output measured here would tell me that I've got 10 amps flowing to my load. Well, because the shunt resistor produces a voltage drop of 0.1 volts at 10 amps, that means that to get to 10 volts, I need a gain of 100. All right? So choose R2 to be 100K and R1 to be 1K, right? Or you could do 1000K and 10K. At this point, we haven't dug into this enough to realize that there's some benefits or trade-offs with the total resistance of R1 plus R2. The main point here is note that R1 is much, much greater than, if this is my sense resistor, I'll call it RS, right? Actually, for this to work well, my R1 has to be much, much greater than RS, which it is. It's 1,000 compared to 0.01, so it's a $100,000 It's off by $100,000. I don't want to say $100,000 because I wish I had $100,000. Yeah. So with 100K here, and 1K here, and 1K here, and 100K here, we have just put to use our difference amplifier to have a capability that of being able to sense a 0 to 10 amp current flow to a load from a battery. And this battery, for instance, could be a 12-volt battery, but it could be, say, a 48-volt battery. If you think about it, at 48 volts, if I'm sensing 1 amp, okay, the voltage going to the positive input, like right here, this guy, we'll call it Vs plus, this would be equal to 48 volts. And the voltage here, call it Vs minus, would be equal to 47.99 volts. This would be at 1 amp, right? And so you're this tiny, tiny difference, right? And yet the amplifier would put out, in this case, 1 volt. Right? So that's the power of a difference amplifier. It amplifies just the difference between the two voltages. So, recapping, we've introduced 3 op-amp topologies. All right, they are the I'm trying to write too fast. Non-inverting amp. That's this topology here. We have VI and a feedback resistor R2 and a grounded resistor R1. And we have VO is equal to 1 plus R2 over R1 times VI. We have the inverting op-amp, and that one is like so. And here VO is equal to minus R2 over R1 VI. And finally, we have the difference or differential amplifier, difference amp, which looks like this. I have R2, R1, R1, R2, and we'll say this is, what did I call this before? V1, I think, and V2. And VO is equal to R2 over R1, V2 minus V1. Now you might wonder, how is it V2 minus V1 or V1 minus V2? That's easy to determine, because the one that goes first here is the signal that's going into the positive, okay? The positive terminal ultimately. Although it's going through a resistor, it's going to the positive. All right? So there's a intro to op-amps, and I think now you're ready, if you use these analysis techniques, to analyze some other circuits in your homework that will just be, small modifications or maybe some combinations of these amplifier op-amp topologies.